Okay, welcome back. Today we're going to look at section 1.11b, which deals with polynomial long division and slant asymptotes. So yeah, let's get right into that. Let's look at number one. Let's see. So anytime we're dividing polynomials, we're going to set this up similar to how we would regular long division. So for example, if I wanted to do like what is 73 divided by 5, I would set this up as how many times does 5 go into 73? So what I do is I ask myself, well, how many times does 5 go into 7? And 5 goes into 7 one time. And then 5 times 1 is 5. So I multiply, note these steps as we do them. So I multiply 5 times 1, and I get 5. And then I do subtraction. I have 7 minus 5, which gives us 2. And then I bring down the next number, in this case 3, and I repeat the process. I ask myself, how many times does 5 go into 23? And we would say 4 times. And then 5 times 4 is 20. I do subtraction again. I have 23 minus 20, which gives us 3. And since I don't have any more numbers to bring down, I would say that our answer is 14 plus our remainder, 3, divided by 5. So if you know how to represent this as a decimal, this would just be 14.6. But I'm going to encourage us to leave it in this form because that's the form that we're effectively going to leave it when we're doing polynomial long division. And so, pretty similarly, if we're dividing out these two polynomials, we're going to do, let's see, so the one on the bottom, it's going to go on the outside. So we have x squared plus 5x plus 1. And we ask ourselves, how many times does that go into 3x cubed minus 4x squared? We have to remember to put 0x right here as a placeholder, and then minus 3. So first we ask, and when we're doing polynomial long division, all we need is just whatever these leading terms are in our division algorithm. So we ask ourselves, x squared times what gives us 3x cubed? And that would be 3x. So then we multiply all of this times 3x, and we're going to write it down here. And this is going to be why this 0x is important for a placeholder. So if we do 3x times x squared, we should get 3x cubed again. If we do 5x times 3x, we get 15x squared. And if we do 1 times 3x, we have 3x. We're going to put parentheses around all of this, and then we're going to do subtraction. So notice that this is 3x cubed minus 3x cubed. If you're doing polynomial long division correctly, this term will always cancel out. So we'll get a 0 out of that. Hold on, let me look at my phone real quick. Okay. So then we have negative 4x squared minus 15x squared. So really this is negative 4 minus 15. So we get minus 19x squared. Then we have 0x minus 3x. So this comes out to minus 3x. And then we can bring down this minus 3. And I'm sure you can hear my cat again. So just like how we did over here with our regular long division, we're effectively at this step with the 23. And what we have to do again is we repeat our process. We ask ourselves, just like how we did over here, how many times does 5 go into 23? Now we're going to ask ourselves, how many times does x squared go into negative 19x squared? And so our answer for that would be negative 19. And so now negative 19 times x squared is negative 19x squared. Negative 19 times 5x is going to be negative 95x. And then negative 19 times 1 is going to be negative 19. And so now we put parentheses around all of this, and we do subtraction. And so be mindful of this negative out here in front. What that's going to do is flip the signs for each of these. So we have negative 19x plus 19x squared, which is going to cancel out. And we have negative 3 plus 95. So that's going to be positive 92x. And then we have negative 3 plus 19. So that's going to be positive 16. And now, since we don't have any other stuff to bring down, we're done. And so we write our answer for this. So writing it in the same form that we had over here, we had 3x cubed minus 4x squared minus 3 divided by x squared plus 5x plus 1. And we would say that this is equal to whatever we have written up here on top, 3x minus 19, and then plus whatever our remainder is, which is 92x plus 16, divided by whatever we were originally dividing by. And that's x squared plus 5x plus 1. And so I want us to note the similarities between these answers, because when we were doing 73 divided by 5, notice the placement of everything. The 73 goes on the inside and the 5 goes on the outside. Similarly over here, whatever we had on top went on the inside, whatever we have on the bottom went on the outside. This number right here, the 14, was the number that we had on top. And this expression here, the 3x minus 19, is also right here. The 92x plus 16 was our remainder, just like over here, 3 was our remainder. And our 5 was what we originally were dividing by. And so we have x squared plus 9x, or 5x plus 1. I can barely read my own handwriting. That was what we were originally dividing by over here. So once we understand the setup and how this relates to, I guess, traditional long division, just with numbers, I think it makes it a lot easier. Also, if we are doing a problem like we have for number 2, where we're ever dividing by x plus or minus a number, we can actually make this process even smoother. So let's try this. We have x cubed minus 4x squared plus 6x minus 4 divided by x minus 2. So we could divide this out like we did with the polynomial long division. However, there's a faster way if and only if we're dividing by x plus or minus a number. And how we set that up is, first, we have to make sure that we can read off whatever the coefficients are here for each of our numbers in the numerator. So we have an implicit 1 right here. We have a negative 4, a 6, and a -4. Also notice that we're in standard form. This has to be in standard form. So remember that means that our exponents are in decreasing order. So we have 3, 2, an implicit 1, and an implicit x to the 0 right here. And we don't have any gaps, like we're not missing our x squared term. So we're pretty much good. This is already just set to go. So coefficients we have are 1, -4, 6, and -4. We're going to put a number out here, and that's just given by flipping the sign on whatever this number is here. So since this is a -2, we're going to flip that to be a +2. And how we do synthetic division is we bring down whatever this number is, and we have a 1. Then we multiply 2 times 1, and we get 2. Then we add whatever these two numbers are in this column. So -4 plus 2, which is going to give us -2. And every time we're going to multiply 2 times whatever this number is. So 2 times -2 is -4. 6 minus 4 is +2. 2 times 2 is +4. And -4 plus 4 is going to be 0. This term right here, or this number, is going to represent our remainder. This term right here is going to represent our constant. This right here, since we're using x, this is going to be our x term, and this is going to be our x squared term. So when we construct our answer from this information, all of this is equal to 1x squared minus 2x plus 2, and since we have a remainder of 0, it's just, well, we don't need to write that. But whatever this value is, if we wanted to write this as, say if this weren't a 0, we would write this as whatever our remainder is divided by, in this case, x minus 2. But again, since we have 0, 0 divided by any number is still 0, so we don't really need to write that here. But that's how we do synthetic division. And so, why we're concerned about this in this topic is because we're going to use polynomial and synthetic division to find the equations for slant asymptotes. So we've seen horizontal asymptotes before, where we have a function that maybe has a vertical asymptote, and we've seen our horizontal asymptotes, but we've had functions before that have an asymptote that looks like this. So it's not horizontal, but it's not vertical either, it's slant. And so very often we see functions that will follow a slant asymptote like this. Still works like any other asymptote, it doesn't touch it. Generally, we have what are called crossing points on it, but we're not really too concerned about that. Basically know that the function's end behavior, so just as it goes towards positive or negative infinity, the function follows that asymptote. And it's absolutely possible that we have a slant asymptote that maybe goes like this, like maybe it still looks like this one over here, but it could come up and then follow it like that. And that's perfectly fine. But again, in general, our function follows the asymptote. We can cross a horizontal asymptote and we can cross a slant asymptote. The only one that our function can't cross, and it never touches under any circumstances, is the vertical asymptote. But with that being said, let's look at the next problem for number 3. So for number 3, we want to use the graph of f to write the equation of the slant asymptote. So for these slant asymptotes, all we need to do is find the the slope of the function. Remember, all of our, at any line like this can be represented in the form of y equals mx plus b. So if we're able to identify the slope and the y-intercept, then we can find the equation of this line. So notice that the y-intercept here is at -1. So that's important information. And now we just have to find the slope. Well, for every 2 that we go over, we go up 1. 2, 1, 2, 1. And so our function, remember that our slope is given by rise over run. And so for every 2 that it goes over, it's going up 1. So our rise is 1, and our run is 2. So we can construct that as y is equal to a rise of 1, a run of 2, so 1/2 x, not plus, minus 1. And so that's the equation of our slant asymptote. Now, what about this one over here? So, again, we note that we have a y-intercept of -1 there. But what about our slope? So we want to find lattice points. So fortunately, this is a lattice point, but our function doesn't really touch another lattice point until about right there. So right there, we can see that, okay, so for every 1, 2, 3, 4, 5 that goes over, it goes down 2. So we have a run of 5 and a rise of -2. So we could say that since we have a rise of -2, a run of 5, we have a slope of -2 over 5x. And then because, again, our y-intercept was -1, that is our equation for our slant asymptote. And so, how could we determine whether we have a horizontal asymptote, a slant asymptote, or neither? Well, I want to look back at both of these problems up here that we did for 1 and 2. Yeah, I'll just tell you. Basically, look at the degree of the functions for number 5. So in our numerator, the degree of this polynomial is 5, and the degree of the denominator is 3. So just to write the degree over the degree, basically, you'll have a horizontal asymptote. We should remember from a previous section that if these polynomials have equal degree, that we will have a horizontal asymptote. Or if the degree on the bottom is bigger, we'll have a horizontal asymptote. But importantly, if they're equal, they'll have a horizontal asymptote. If the degree on the top is exactly 1 higher than the bottom, so if the bottom is 3, we'll have a slant asymptote if this is degree 4, but this is degree 5. So if it is anything bigger than exactly 1 of the degree of the bottom, then it will not be a horizontal asymptote. It won't be a slant asymptote. It'll be a asymptote given by some higher degree polynomial. In fact, it'll be given by this function will have a parabolic asymptote because 5 minus 3 is 2, and a second degree polynomial is a parabola. But we would say that this does not have a horizontal or a slant asymptote. Now, if we look at the degrees over here, degree of the top one is 4, degree of the bottom one is also 4, And so since the degrees are equal to one another, this is going to have a horizontal asymptote. And then we have a degree of 3 over here. And then we have a degree of 4 on the bottom. And remember, if the degree of the bottom is bigger, then it will also be a horizontal asymptote. So we only have a slant asymptote if the degree of the top is exactly 1 higher than the degree of the bottom. So if this was degree 4, this would be a slant asymptote. If the top one of this one was degree 5, this would be a slant asymptote. And similarly for this one, if this one was degree 5, this would be a slant asymptote. And so, even if we look at these over here, for number 1, the degree here is 3, and the degree here is 2. So 3, 2, 3 is exactly 1 bigger than 2. This has a slant asymptote. In fact, the slant asymptote is given by whatever we have right here. So whatever this answer is gives the equation for your slant asymptote. On the other hand, for number 2, the degree here was 3, and the degree here is 1. So, exactly 1 bigger than 1 is 2, which is not 3. So, this is not a slant asymptote. However, what kind of asymptote is it? Well, when we did our synthetic division, this right here is our answer. This is actually the equation for our asymptote. And as I said earlier when I was looking at number 5, this is a parabola. Notice that 3 minus 1 is 2, so second degree polynomial. Our asymptote is a parabola. All right, so let's look at the next few problems. The next few, we want to write the equation for the slant asymptote of the following functions. So really, all we have to do is do our polynomial long division or synthetic division, depending on which calls for it. And then that will tell us what our asymptote is. So looking at number 8, we want to know how many times is x squared minus 2x plus 1. How many times does that go into x cubed minus 2x minus 4x plus 1? So we ask ourselves, well, how many times does x squared go into x cubed? Or in other words, x squared times what gives us x cubed? That would be x. And so we multiply all of this by x. That gives us x cubed minus 2x squared, and then plus x. We put parentheses around all of this, put a minus out in front, and then we do subtraction. Remember, this minus is going to flip all of the signs of the inside of the parentheses, so we have x cubed minus x cubed. That will cancel out. We have negative 2x plus 2x. That also cancels out. And then we have negative 4x minus x, which is minus 5x. We bring down the plus 1. And notice that x squared doesn't go into negative 5x at all. So really, this is all of our remainder. And all of this right here, just the x, that's the equation for our slant asymptote. In fact, if we were to write out the full answer for our polynomial long division, we would say that x cubed minus 2x squared minus 4x plus 1 divided by x squared minus 2x plus 1 is equal to x. Oh man, my cats are fighting. It's equal to x, and then minus, well, I'll just write plus, just to keep it simple. Negative 5x plus 1 divided by x squared minus 2x plus 1. And this would be our final answer. But again, this part right here, what we have up top, is our answer for, that gives us the equation for our slant asymptote. So I guess if we wanted to write the equation for that, it would be y is equal to x. And so we can even graph this so that we can see. So if I go to graphing calculator and I type in this function, I'm going to do, so we have x cubed minus 2x squared minus 4x and then plus 1 divided by x squared minus 2x plus 1. And then I want to graph y equals x. And let's see what this looks like. So we have our polynomial. And look at that. So, well, not our polynomial, our rational function. But look at the asymptote. It goes right through. And even if we zoom out, now it looks like the asymptote is touching because the calculator doesn't have a high enough resolution. But as we can see, the asymptote, or the function perfectly follows the asymptote. And so if we zoom back in, the other point I wanted to make was, remember, I mentioned we have something called a crossing point. Won't be really necessary for us to know that, but as mentioned, it is possible for our function, for our rational function to cross the slant asymptote as it does right here. That doesn't really signify anything, but just pointing out what I did earlier. Okay, let's look at the next one. So for the next one, we have, we're going to do number 9. So we have x squared minus 9x plus 4 divided by x plus 6. Fortunately for this one, we can set up with synthetic division. So again, remember that's just read off the coefficients that we have here. So we have a positive 1, a negative 9, and a plus 4. So we're going to set that up with a little box like this. We have a 1, minus 9, and a 4. And then we have a minus 6. We have to flip this sign every single time we do synthetic division. But then we bring down whatever this number is, in this case 1. We have negative 6 times 1, which is negative 6. We have negative 9 minus 6, which is negative 15. We have negative 6 times negative 15, which is positive 90. And then we have 4 plus 90, which is 94. So, remember, this is our remainder, this is our constant term, and this is our x term. And so we say that the answer to this is x minus 15 plus, in this case, we did have a remainder, so 94 divided by x plus 6. But since all we wanted was the equation of our slant asymptote, this part right here is all we needed. So y equals x minus 15 is the equation for our slant asymptote. Okay, let's look at the next one. So for the next one, number 10, we can, now I've said that we have to do this, or we can only do synthetic division if this is x plus or minus a number? Well, we can force this to be in the form of x plus or minus a number. If we divide both the top and bottom by 2, it will change it into an acceptable form for synthetic division. So first, let's see how we do that. We have 4x squared plus 12x minus 6 divided by 2x plus 1. And notice, if I multiply the top by 1/2 and I multiply the bottom by 1/2, this is going to give us 2x squared plus 6x minus 3 divided by x plus 1/2. So that 1/2 isn't going to be very fun to deal with, but that will make do. So now we can do synthetic division with this. And so let's see what we do. So first we got to set this up. So we're going to have a 2, 6, and a -3. And then on the outside, we have to flip this sign, and we have to make it, just, this number, but flip the sign. So this is going to be a -1/2 outside. Then we first bring down this number. We have a 2. -1/2 times 2 is going to be -1. 6 minus 1 is +5. -1/2 times 5 is going to be -5 over 2, or if you prefer, -2.5. And the -3 minus 2.5, it's going to be -5.5, or as I would prefer personally, -11 over 2. And so this is our remainder, our constant, in our x term. And so we would say our answer to this is 2x plus 5, and then minus, we could write -11 over 2 divided by, remember we divided by x plus 1/2, so we actually can't write 2x plus 1. So x plus 1/2. However, what we can do is, because this is terrible looking, we have fractions in our fractions, and we don't like that. We can multiply both top and bottom by 2. We don't need to do that over here, but we have, for our answer, we have 2x plus 5 minus -11 over 2 times, -11 over 2 times 2. That's going to cancel out. This is just, that's going to be 11. And then, remember, this is all of this by 2. We have 2x and then plus 1. So that was, again, what we were originally dividing by. But what we wanted was the equation of our slant asymptote, which is just given by this piece right here. So we have our answer as y is equal to 2x plus 5. This is the equation of our slant asymptote, and we are done. Let's look at that last one. So for number 11, we have 9x to the 4th minus 5x squared plus 3x minus 6 divided by 3x cubed minus 4x squared. So when we're doing our polynomial long division, again, we have to make sure that we don't have any gaps in our terms. So we have an x to the 4th term. I mean, this is in standard form, but this goes from x to the 4th to x to the 2nd. We're missing our x cubed term. So when we're setting this up, we have to be mindful of writing that in. So we'll have our 3x cubed minus 4x squared, but when we're writing out what goes inside our whatever that symbol's called, I don't know. We have 9x to the fourth plus 0x cubed minus 5x squared plus 3x minus 6. And then we ask ourselves, how many times does 3x cubed go into 9x to the fourth? Or in other words, 3x cubed times what gives us 9x to the fourth? And that would be 3x. So then we multiply 3x times all of this. This is going to be 9x to the fourth. And then we have negative 12x cubed. Again, why that placeholder is important. That way we keep all of our terms in line. But we do some subtraction. This cancels out. And remember, this minus will flip all of the signs in here. So we have 0x cubed plus 12x cubed, which is just going to be 12x cubed. We bring down our next term, which is the minus 5x squared. And then we repeat. We ask ourselves, 3x cubed times what gives us 12x cubed? And that would be plus 4. So we multiply all of this by 4, and we get 12x cubed minus 16x squared. We do our subtraction, we have that, cancels. The minus is going to flip the sign on this, so we have negative 5 plus 16, which is going to be 11x squared. And we could keep going and do, blah, blah, blah. But remember, this is just going to be our remainder down here. And really, since this is already a constant term, it's just going to be the plus 3x minus 6. We would just bring all of that down. But if we're just trying to find the equation of the slant asymptote, really all we needed was this part. And so we can just stop right there, and we can say that y is equal to 3x plus 4.